I'd like to talk about particles and waves, and to do that, I want to talk a little bit more about wave functions. Suppose I choose an observable, operator L, that has eigenvalues lambda and eigenvectors or eigenkets lambda ket. And let's let psi, capital Psi, be a state vector. Since eigenvalues of a Hermitian operator form a complete orthonormal basis, we can expand psi in terms of those basis vectors as sum over lambda psi of lambda times ket lambda. Psi of lambda is what we call the wave function for the system whose specific form depends upon the form of the observable L. So it's in the L basis, so to speak. If I picked a different operator, then I would have a different wave function and different basis vectors, even though I might be describing the same exact state. So what we'll call it, we'll say that psi of lambda is a wave function in the L basis. What are the other properties? Well, orthonormality dictates that psi I, psi j is Kronecker delta ij. In other words, the vectors are orthonormal. If I is not equal to j, then the inner product is 0. I can identify psi of lambda in the L basis with the inner product of vector psi and its eigenvectors lambda. So I can write psi of lambda is equal to the inner product of lambda and psi. There are two ways we can think of this. We can think of wave functions in this way. I can think of it as the set of components of a state vector in a particular basis. I can stack up the components like so. I might write them as psi of lambda 1, psi of lambda 2, psi of lambda 3, psi of lambda 4, etc. Or this nice 1x4 matrix, or 4x1 matrix, I should say. Or I can think of the wave function as a function of lambda. So if we specify lambda, the function psi of lambda produces a complex number. So psi of lambda is a complex valued function that has discrete value variable lambda. And this way we can say linear operators are applied to functions and give back new functions. And the probability for an experiment to have some outcome lambda is just v of lambda, or psi star of lambda times psi of lambda. So that's why we can think of wave functions. That's probably familiar to you from modern physics, but it's worth seeing under the this sort of linear algebra format as well. So we're going to talk about functions as vectors. So we'll go from finite dimension, where you might be talking about spins in two-dimensional spin space, to infinite dimensions, where I might be talking about the x position of a particle, because it could be anywhere. It could have any infinite number of locations. X is going to be a continuously infinite variable, so the wave function becomes a function of continuous variables. Now, functions can form a vector space a complex vector space that we call a Hilbert space. Hilbert spaces can be finite or they can be infinite. So functions like psi of x are going to satisfy mathematical axioms that define a vector space. Notice the complex vectors satisfy all the requirements that define a complex vector space. So in other words, we can say that the sum of any two functions in that space is a function. We can say that the addition of functions is commutative. We can say that the addition of functions is associative, just like we did earlier. We can say that there's a unique zero function such that if I add it, if I add psi of x to 0, I get psi of x back. Now I can talk about the fact that there's a unique function minus psi of x such that psi of x plus a minus psi of x gives me 0 back. I can multiply that function by a complex number. Let's call it c times psi of x. And that just gives me another function called c psi of x. And then the distributive property holds as well. And we can show that in two cases. I can say that z is a complex number, psi of x and phi of x are two functions. That's just going to be equal to z times psi of x plus z times phi of x. And similarly, if z and w are two complex numbers, when I multiply by psi of x, I'll get z psi of x plus w psi of x. All these guys are going to be functions. So it looks very familiar to the linear operators that we talked about before. So we can identify my function psi of x with ket vectors psi. And by the same, in some abstract vector space, I can also identify psi star of x complex, psi complex conjugate as equal to as being identified with the bra of psi. So it's all kind of self-consistent. It's not that they're equal to one another. The mathematicians might say that there's an isomorphism between psi and ket psi, or psi star and bra psi. Now, if we talk about continuous variables like position, we're going to have to do a few things to change the game. Let's talk about that. So we're going to have to do three things when we go from discrete to continuous functions. First of all, we have to replace the sums with integrals, of course. You're used to seeing that trick in plenty of your courses. We're going to replace probabilities with probability densities. And thirdly, we're going to replace our Kronecker deltas with Dirac delta functions. So what does that mean? Under this first replacement, inner product psi is going to be written as minus infinity to infinity psi star psi of x dx. So my sum now is an integral. Under number 2, my probability is just going to be psi star of x times psi of x. And since the total probability is equal to 1, it has to be that if I integrate over all space, psi star of x, psi of x dx, that integral must equal 1. That is, if the distribution is normalized. And under number 3, where I replace Kronecker deltas by Dirac delta functions, I have something like this. When I have a discrete case, when I have a Dirac delta function, it's like minus infinity to infinity, x minus x prime, f of x prime, dx prime is equal to f of x. What it does, the delta function does in an integral like this, is it picks out the one value of x, of the function at x prime equal to x, and that's what the result of that integral is. Anytime you see a delta function, it sort of lives to be integrated, and as you'll see when we go deeper into this course. Now the area, you want to think of a delta function, it's not really a function, but the area under the delta function curve is always 1. And you can envision a function, not really a function, but an entity that has a very, very infinitesimal width and an almost infinite height, and such that the product of the two gives you 1 as an area. It's a very, very useful entity in physics, and you've probably seen it already, but you're going to see it a number of times in quantum mechanics as well. By the way, a neat function that approximates a delta function is the function n over square root pi e to the minus nx quantity squared. That's a pretty good approximation to a delta function. You use that occasionally. One other trick that we have up our sleeve, you might remember, you probably learned in Cal 2, or maybe it was Cal 1, the technique of integration by parts, where you integrate a function, u dv, and that's always equal to uv evaluated at its limits minus the integral of v du. Sometimes that makes solving integrals easier. Whenever we do integration by parts, well, maybe not always, but almost always, this surface term almost always vanishes. And so we have a very simple expression, an equivalence when I integrate by parts of u dv equal to minus the integral of v du. It's useful. It's a useful thing to remember. So in other words, I can write something like the integral of minus infinity to infinity of f times the partial of dg, well, maybe total derivative dg dx. Dx can be written as minus the integral of df dx g dx. If I'm using partials, I guess I use partials. Okay. So that's another nice tool to put in our arsenal when it comes to sort of math tricks that can make our lives easier. I would like to move on to continuous operators such as the position operator. Now this is going to sound a little strange the way we describe it, but it's nice if we can stay consistent. Suppose I have a position operator, x hat, such that if I apply x hat to the wave function psi of x, it returns some value of x, that the actual position of this object, times the wave function psi of x. We can define, let's define D as a differentiation operator, such that if I operate on psi of x with my differentiation operator, I'm going to get d d psi of x dx. So we're talking about two kinds of operators that seem a little strange when we put it in these terms, but I think that you'll see that some nice things will evolve from this. I want to talk about hermeticity for a moment. This is kind of important. I can sandwich an operator L in two ways. I can put it between between ket raw psi, ket t. Or I can do it the other way. Like so. But there really isn't a simple relationship between these two guys unless L is Hermitian. If L is Hermitian, then I can write this nice relationship between the two. Where one is just the complex conjugate of the other. These are two matrix elements, and of course they're just complex numbers. And it turns out that one is the complex conjugate of the other. Turns out that x is a Hermitian operator. On the other hand, d is an anti-Hermitian operator. In other words, d complex conjugate is equal to minus d operator instead of being equal to d operator. It's anti-Hermitian. But it turns out we can construct a Hermitian value or Hermitian version of d by simply multiplying by minus I times h bar. If I do that, and the h bar comes in, as you'll see, it's going to be very useful to us. If I do that, I will turn d from a anti-Hermitian operator to an Hermitian operator. And in fact, we'll be using this expression to describe momentum very shortly. If you remember back to your classical mechanics or statistical mechanics, we talked about phase space. And in phase space, remember we looked at it as a sort of a graph between momentum and position, and we could describe some coordinate in phase space by establishing a grid, and any point on there would be a point in phase space. You might think that the quantum mechanical equivalent would be to say, well, why don't we just have something like x and p, two kets? That's not legal. It would be a wrong way to think of it because we can't know simultaneously x and p. As you'll see, by the Heisenberg uncertainty principle, we cannot simultaneously measure x and p. The more I know about x, the less I know about p, and vice versa. Let's take this a little bit further and see what we get. Let's just go back to the position operator and ask, what are the possible outcomes of a measurement of x? Well, here's my x operator, and I'm going to operate on some ket psi. I expect it's going to give me some eigenvalue, some position. I'll call it x naught times that ket. Or if I want to do it in terms of wave functions, I can operate on psi, and it's going to give me x naught psi. This looks a little crazy, but let's go ahead and subtract one side from the other. And I have this expression. What it's telling me is that if x and x naught are equal, this equation works. Because surely I don't expect my wave function to be 0. So what that's saying is, for a given eigenvalue x naught, this function can only be can only be non-zero at x equal x naught. Well, can we think of a function that's 0 everywhere except at one point? And we go back to, of course, the Dirac delta function. Delta of x minus x0. This is 0 everywhere except when x is equal to x naught. So if I use that, that actually picks out the point that I'm interested in. If I want to say the position that I want my particle to be at as x naught, a way I can describe that function is, hey, I'll write it as delta x minus x naught. Because the only term that survives, if I sum over all x's, is going to be the one that x equals x naught. Now, let's consider the following unit product. X naught psi, where x naught is a position eigenstate. I can write that then as the integral, because I'm going to use the Dirac delta function, x minus x naught psi of x dx, integrated over all space. And of course, the delta function serves to pick out that value where x is equal to x naught. So this gives me psi of x naught. And since this is true for any x, I can just drop the subscript and just say x psi is equal to psi of x. So the wave function of a particle moving in the x direction is the projection of the state vector psi onto the eigenvectors of position, x, in this case x broad. Psi of x is the wave function in the position representation. So this is wave function in the position representation. Suppose we wanted to do it not in terms of position, but in terms of momentum. Can we talk about the x position in terms of a momentum space? Let's define the momentum operator as minus I h bar d, so that p applied to psi of x is equal to minus I h bar d psi dx. I can write my eigenvalue equation. P psi is equal to little p, my momentum eigenvalue psi. Or I can say minus I h bar d psi of x dx is equal to p psi of x. Or, take it a step further, d psi of x dx is equal to I p psi of x divided by h bar. Well, it looks like a differential equation, doesn't it? Yeah, the solution, of course, is psi p of x is equal to some constant a, integration of constant I p x over h bar. We can fix a by normalizing the wave function, and in this case it turns out to be 1 over the square root of 2. So this is the momentum eigenfunction in the position basis. I want to continue this next time, and we'll take this further and talk about how position and momentum are actually the Fourier transforms of one another. We'll develop that in the next lecture.